Our project was the elevator people counting. This is just the update. I can just press these.
Yeah.
Yeah. So basically, the problem is that we're trying to count people like and collect data for like real life elevators, like on school. And what we want to do is we want to be able to count very efficiently the people. And the idea is that eventually we'll have like smart automated systems for elevators to know like if people are actually on the floor. And we have to do this on edge AI, so like on super efficient hardware. So like AI can be powered by like super like data centers, and that consumes enormous amounts of power. But if we want really smart systems and like every facet of our lives, we have to find ways to condense like our systems and our AI hardware so that it's very efficient. And also it's like a privacy concern, because if we have this kind of like camera system and smart systems, it's important that like as the school, for example, if you're collecting that camera data, it stays on the hardware. So for our data set, we so far just collected some data from RoboFlow. It's a very good website for like robotics and for annotation, because like for example, like with all of the data set we collected, it was automatically annotated partially by their systems, and you can also annotate it yourself as well. And so that was like very good. So what we did is we collected about 13,000 images so far, and we converted this to monochrome representation, because for people counting, the color representation it doesn't really matter for that great of a score, and you have the potential for like more efficient inference because you have smaller features to analyze. And we also downscaled it a lot, so we don't actually need that like large of a dimension either. So we found that 192 by 192, that was like good enough to get decent like inference scores, and it was also necessary to get a good frames per second, since that was one of our key points of it, like one of our necessary metrics to satisfy. We also, some of the dimensions were different, so we just added padding to a little bit of them, and we publicly released the data set to Hugging Face, so it's also accessible. I do have my device, but it might take some time. I was able to kind of show like a picture of me. That's the device right there. I might pull it out at the end and show you guys as well. But I was able to just count myself so far. But so far we've only been able to we've only trained on this data set, so it might not be generalized just yet. But it was able to count me here, so I was just able to demonstrate that. So for the model, what we chose to use was this is actually the baseline that was given to us like through code that Nubaton already had ready. So this is like a YOLO model, you only look once, and it's like a miniaturized version, and it's been optimized specifically for our device, the device that they gave us, the M55M1. And so this was able to run. So what we have here is like our input is just the regular frames that from the data set, and so we feed that into the model, and then that goes through the architecture, and then we're just predicting basically if we see a person, and we're also predicting like the where they detected, like the box in which they're detected. So for our training, what we just did regular stochastic gradient descent. We use pre-trained weights, so there's already a very good model they provided to us, which had some good knowledge baked in. We just trained it for an extra 10 epochs. We did some warm-up, we did some cosine annealing, and then we had some default augmentations from Ultralytics. They work on like the model like in a proprietary way, so they have a very good library setup. So we just use their defaults. And once we trained the model, and to deploy it onto our edge hardware device, we had to convert it into Response. That's an open source format, and then we use their then we converted it into like a even more calibrated file that is as we converted from floating point 32 to integer format, and that way it's like a lot more efficient. So after that conversion, we also used the library from Nubaton to further optimize it for our specific edge device. And then we have to physically put that on the SD chip, and then we have to physically build like the the environment so that the chip can actually run it on inference. So we used, I just used VS Code. VS Code, they're developing like for the future. I think it's like the platform that they're working on where it's like the most up to date, and you're able to use just VS Code to build the whole environment. And you can upload to the chip and monitor the chip. So it's very good. And that's basically what is all within VS Code. Very easy. And basically, on our data set, we were able to get really good results. We were able to get good precision or recall, and we were able to get like good detection. So this measures basically how accurate our like detection was, like for detecting people in the area that we detect. And we just barely got like a good frames per second. This was also the baseline, so our requirement was 15 frames per second, like for a good industry standard. So we were able to run this nice. So basically, that's a good baseline so far. Now we actually have to collect like the real data from the elevators, and we have to augment like our initial baseline with this data, and we have to make sure we get like really good accuracy on that collected data. So the next steps are that we're probably gonna purchase a camera, and then we're gonna augment our data set, and we'll feed it through the same baseline system, and we're gonna just make sure that we have good accuracy. So right now the code is all available if you want to try it out as well. And so I don't know if we have time for a demo as well, like 3 minutes.
You have 8 more minutes in your slot after.
Oh, okay.
You're 3:05 to 3:20. It's 3:12.
I see. So yeah, I can just show you guys the chip. So this is basically the chip that we have to deploy this model on. So you can see like it already has the camera like basically built onto the top. Yes, sir. And yeah, and the LCD screen. So you can see it's like a super it's modular. You're meant to like fit this right into like the elevator, like on the top or something, near the system. And I have the camera like slapped right onto there, so that's how I usually do it for testing. But we'll have to find a way to connect a different camera as well. So it has like a bunch of different connectors. And so I'll try and I'll plug this in. And so since I preloaded the model on there, once it kicks up, it automatically starts. So it's like not a very complex operating system. You're meant to like flash the model directly on this device, and the sole purpose of this device is to basically just kick up this one model and like conduct inference. So here I have I'm monitoring the frames per second at 16 frames per second. That's pretty good. But right now it doesn't generalize very well to seeing you guys. So it detects 0 people. So we basically just trained on overhead views. We could augment the data even further to maybe it might generalize better if we do just straight person detection as well. But for now, this is what we have, and it's also monochrome. And you can see it's inferencing directly on 192 by 192 dimensions. So and it captures most of you guys. So that's pretty So basically the intuition is if you can detect it, then it is detecting some of you guys actually.
Can I see if it sees me?
Let's see.
Oh, that's cool.
That's gotta be your let's see.
Oh, there it goes. That's pretty sick.
So the idea is I have to fine tune this on exactly one kind of environment in an elevator, and then it'll be able to detect you at 95% accuracy. So so our explainers are just going to collect some more data. We're going to bake it into the model. We already have the pipeline ready, so that should be good to go. Do you guys have any questions?
So you're using data augmentation, which you just train on more data, you just flip it.
Exactly. So basically that 13K that gets translated into about it's representative of 50K. Because once you do all the augmentations, you get way more value out of your data. So we can actually do more. I just use the defaults, but I can always toggle more. Okay. What's good is that this company, they work on this proprietarily. So
they give you access to some of their proprietary stuff?
Oh no, or it's just free and open source because they want you to use their models, and then if you're using their models, then you want to consult them. I'm pretty sure that's Ultra Linux. That's who works on YOLO. So it's pretty good.
Any more questions for this project?
Then we're doing a PSD plot, which is like basically power density. And so what this is doing is we're validating like the frequency domain by comparing the distributions across the 12 channels for the EMGs. And then we have a random forest classification. And basically we're saying how good is the synthetic data at pulling a classifier. So basically if we're able to make the classifier perform worse at 50, have the classifier get 50% accuracy, that means that the synthetic data is very good at generating realistic data. Or sorry, that the generator is very good at generating realistic data. And then there's an RMS plot, and this is basically just comparing like the strength of averaging muscles connections over. Oh, I sorry, I mistyped. This should be 12 channels, not 13. So for our baseline, we started with basically your average WGAN GP. So we had a couple convolutions, like 1D convolutions for the specific data, convolution transpose and critic, basically just judging how well the generated data is. So the baseline model does not perform very well for this specific data, and you guys will see in a bit the actual outputs of the baseline data. So some things we did to fix this: we adjusted the hyperparameters. There was also an issue. We were trying to follow this paper in which they did masking for certain channels in order during the pre-processing, and that we had issues with that, so we just removed it. We had an issue in which the critic was way too strong. So the critic would basically, the generator would have a really hard time learning how to generate real data. So the loss would be really high. And so it just wasn't very good overall. This is basically what it looked like. So the PSD right there is not very good. The generated data is pretty bad. And that's just an average of all of them, right? So it's not good. And then the losses you can see, so for GANs, they're supposed to fight each other. That's what they're like adversarial neural networks, right? So they're supposed to be fighting, but as you can see, like the loss is like 100 and negative 100. It's pretty bad. So after our tweaks, like removed masking, tweaking the hyperparameters, we got a much better like PSD, and the losses looked a lot better, right? So as you can see, the generator started off pretty high because it was just learning, and now then it gets lower and lower, or then it kind of goes lower, up and down. Basically, it's like it's fighting with the critic. So this was decent, but as you can see, like the PSD is like okay, it could be better. And so the current architecture that we're using right now is we're using the generator as it still takes in labels. We changed from using convolutional transpose to using upsampling, right? And we also adjusted it to have like a multi-head architecture. So it's not like a transformer multi-head architecture. What it's essentially doing is so in the data set, they had specific electrodes, like 1 through 8 electrodes were specifically placed on the forearm. So what we did is we grouped these specific channels. So 1 through 8, all these channels were basically grouped together. So the weights, because the idea is that like the generator is going to generate similar, like the data for forearms are going to be similar across the channels, right? So for those 8 channels, it should be relatively similar because their electrodes are placed on the forearm. So what we basically do is we're saying, okay, generator, like this is basically these channels 1 through 8, kind of group these weights together because they should be similar in the output. And as you guys will see, it kind of works decently well. And then we also have, and something else we do is we do this thing called like, we have like a trunk or like kind of like a box of like all the gestures, right? And so what we do at first is we're giving the generator a basic idea of like, okay, what should like EMGs kind of look like? So a way to kind of think about this is like so typically WGANs, they start from random noise, pure Gaussian noise, right? But now we've given it like if we're like an artist, right? So I'm basically giving the artist a label. I want you to draw like a tree, right? But you're giving the artist and he's like looking at a blank piece of paper. But using this kind of like box technique where we're boxing up the gestures, we're giving the artist an outline. So now the generator has this outline saying, okay, I kind of know what you want me to generate. Let me do that. And then those are done for like this specific channel. So like 1 through 8 were just electrodes specifically on the forearm, and then the other 4 were just placed on different parts of the arm. I forget the like technical terms, but that's pretty much how the architecture for the generator is working. And then the critic, I didn't really change that much, just made it a little bit deeper. So we still take some labels, right, which are just concatenated to the channels. That's why it's a 13 channel. The 13 channel is basically holding the labels. And then we use instance normalization, which is basically trying to help isolate the specific EMGs, right? Another thing that we did was spectral loss. And so what this is doing is like, we're basically saying, okay, because WGNGP works on like the Wasserstein loss, right? But now we're adding the spectral loss. So it's now the discriminator is going to say, okay, I know that this is a fake synthetic EMG, and that's all the generator gets, right? If we didn't use spectral loss, it's basically say, okay, the generator's like, okay, you tell me it's fake, but now I got to figure out how to fix it. Using the spectral loss is basically saying, okay, now I know it was fake, isolate what was wrong. So the frequency may have been a little off, right? Maybe I was generating the frequency a little too high or a little too low at this specific time. So now let me adjust how I'm going to generate the next iteration, right? That's basically how it's working. So it's kind of saying, okay, I have more of like a hint. So it's like having a private tutor. Like, so say you have like some say you're trying to like, you get back your test, right? And you get like, oh, I failed. But now it's like, okay, the private tutor is saying, okay, this is exactly where you went wrong. And it's supposed to help the generator learn overall. And then we our optimizers. So the issue was with that the critic was too powerful. So we just adjusted the critic's learning rate specifically to be slightly slower than the generators. And then we also added like scheduled loss. So basically just decaying the loss over time. It's just like some standard. And this is basically the current output. So this is the TSNE, right? As you can see, it's kind of hard to read. And the reason it's like that is because a lot of the electrodes or like the EMGs kind of like overlap with one another, right? So like a lot of the signals kind of look the same, which is why like it's really hard to work with this kind of data because like it's hard to generate something that like looks so similar to other things when even though like they're different, right? Here is like the RF classifier. As you can see, it's not that good. It's like got a 90, so the classifier is still able to basically say, okay, I know 91% of the time, like I'm correct. Like I'm basically, the classifier is able to tell, okay, I know that this is fake data, like pretty easily. So that's something that we need to work on. And this is just the PSD channels PSD per channel. And this actually doesn't look too bad. As you can see, some of the channels are pretty like accurate in terms of like the like real EMGs, for example, but like some of them aren't that good. Like channel 3, right? As you can see, it's like kind of like below or dip below. So it's not super accurate for some channels. So we have like an issue at like the higher frequencies, right? So it's not like, for instance, when you're like, closing your hand, it's kind of having a hard time understanding that. But overall, this isn't that bad. And this is just the RMSE square error. So this is basically like if you want to think about this like volumes, right? So for instance, when we squeeze our hands, right? Is it doing a decent job, and it's doing okay. Like this is like, it looks decent, right? But it's RMS is like maybe not like the best because of the math that's being done to use that, right? So root mean square error, like you're just taking the kind of y1 minus y2 squared, right? Squaring it. So like this is decent, but could be a little bit better. And also we need to train on like a wider variety of exercises because this is only done on one exercise set. So we need to train for like different subjects, different exercises as well. So overall, like we've got like a decent model going. So we need to tweak some of the hyperparameters to hopefully get it to do better, and also just work with more data. That's pretty much it.
You guys have any questions for the presenter?
Yeah.
What are the applications of this? By the way, great job.
Yeah, so for instance, it's really hard to get medical data, right? That's one application. So for instance, I don't know if you know, like I tried to get like a cancer data set one time, and I had to like fill out this form, and it's kind of like a hassle because like privacy, right? Like I can't, like it's like, for instance, I need data from the hospital. I have to go through this like thing like saying, okay, this is what it's going to be used for, right? And it's kind of a pain, and sometimes they won't even let you just for privacy issues, right? Another thing that it's could be useful for is because it's really hard to generate these like very accurately, being used to kind of help say like I have an electrode, right? So and it's on my arm. But like, say I have like a prosthetic, and like I'm sweating, right? So like, then like that electrode's not going to send like the proper signal, so it's going to fall. Like once some of these electrodes stop working, you're not going to be able to use your prosthetic. So if we can use like a synthetic EMGs to kind of say, okay, this is what the should look like. The EMG should look like for this electrode specifically. Then you should still be able to use your prosthetic, even though like the signal's kind of wonky or not as good, or even like gone, right? So say like I had like some electrodes on my forearm, and then like I'm like this one person was actually I forget the company off the top of my head, but they had like this guy who had their prosthetic. He was working in an attic, and he lost use of his arm because like he was sweating a lot because it's really hot in an attic. And so it was like, okay, now he can't use his arm, and he's like in this attic. So the another kind of application is being able to, okay, so even though I lost some of the electrodes, like let's generate it to hopefully you don't lose like use of the prosthetic.
Yeah, that's cool.
Alright, thank you guys. All right, very cool project. Thank you guys. Very interesting, very high level, very good stuff. Please welcome Rashid and his project Claire.
Thank you, bro.
All right. Hello, everyone. My name is Rish. I'm joined by Jeet, Stephanie, Vladimir. These are just some of the team leads at Project Claire. So really quickly, I want to talk about like what Claire does, because I know most of you in this room weren't really present for my actual pitch because I did it on like week 2. So essentially, Claire is an app where users are able to like take pictures of like their face if they have like some sort of acne problem, and we'll have like a CV model where users can get responses on like what exactly they're dealing with, what products may help them, and some habits to add to their routine. And the idea is that it's like highly personalized to like who you are. You create an account and you're like, oh, I have like oily skin or dry skin, and current things that you're dealing with. And yeah, that's the idea of just have an app that will help you from just snapping a picture. So far, I mean, thankfully we have like a lot of hands on deck, so we were able to make a lot of progress. For our MVP, our minimal viable product, we just wanted to not focus on training our own computer vision model yet, but using an existing multimodal model and just working on the app first. So far we've pretty much finished everything for our MVP except for our front end. So unfortunately I can't really demo anything today, but we can go in depth into like what we built so far. And we've tried to stray away from vibe coding as much as possible because this is a learning experience for our group. So the front end did take some time, and we wanted to build it last so it perfectly matches the features that we have in our back end. But the way so far we've completed our entire back end, including the database and like the API calls and things like that. Our AI team has completed the RAG pipeline and implemented the model. The model that we're using for our MVP is actually OpenAI's 4.0 mini model. So it's like a cheaper model that actually has pretty good accuracy, like baseline for it. It's around in like the 80%. And in our like testing with like a demo web app, we've noticed about like 93% accuracy so far. So that's a good sign. And we've also completed curated a database for like all the dermatology related things that includes like knowledge, images for the future for computer vision. I'll touch more about that in the future, but that was probably our most challenging aspect because data is hidden behind like paywalls, and legally are we allowed to use some of the databases out there. So it was pretty challenging, but our data team was able to get it done. So I guess we have Stephanie here, our backend team lead. So she'll be talking about everything that was completed in the backend a little bit more in depth.
Yeah, so I'm gonna first talk about the database. So we had stuff like the users, the profiles, and also a little into like the AI&ML, like the chunks and embeddings. And I think the challenge that we had for the backend was kind of like determining what we needed for the database. So we talked with the data and AI&ML team a lot to decide what we need for the database. And then for the backend API, we basically had the API sort of store in the database, kind of get stuff in the database, and we have things like the user profile, the ask question, which would basically get information from the user profile database, and then kind of call the route backend to get the result.
Sounds good. Yeah, Stephanie's the GOAT, y'all. So the way our MVP works currently is, on our mobile app, the user, can either ask like a question, just like plain text, or they can snap a picture or upload an existing picture currently. And then, we will authenticate that image. We'll check for like related context that's in the user profile already. And then we have the RAG layer because, like I mentioned, we have a lot of knowledge docs. It was pretty difficult to find a lot of information about that. But there were like databases out there like Paula's Choice, for example, has a Beautypedia with a lot of skincare related, ingredients that are in products and, what they do, their effectiveness, if they clash with other products. So because we don't really have anyone with like a full medical background on our team, it was important for us to make sure like all that information was right. The RAG layer will talk to both like our knowledge base, which is pretty comprehensive at this point. I think we have around like 170,000 records, like just combined from different sources. And then on operational data, that's like the context that Clear has from users over time. When a user makes a request, I kind of went over this. It's the skincare ask endpoint, image validation, the RAG. The RAG is formatted with a bunch of JSON, and then log. We have a history endpoint, so the app actually will keep track of progress over time. It could show you like visual changes if you opt in to allow those images to be stored locally on your device, and it can have like a timeline to show you your progress, any challenges, like any setbacks that you may have, like any inflammation, if you might need to change up your routine. So I think that's like the whole personalization aspect of it all. Challenge one was the ingredient and product coverage. I did mention, we pulled some information from Paula's Choice and other databases that were publicly available online. We tried our best to stray away from things that were, not like free or legal for us to use, that weren't in like considered educational or research purposes and stuff like that. There were some good databases about from Stanford as well. But a lot of them did involve like things like melanoma, not really skincare related, but we decided it's best to actually include it in our database because, in the case that a user does have like skin cancer and a melanoma and uploads it to Claire, one of the important parts that we wanted to enforce in our like whole AI guardrail thing was to escalate to a doctor when it's needed. So we can't just tell someone with a black spot on their hand, like, oh, this might be a blackhead. No, like, if it looks like a melanoma, we definitely need to warn the user and tell them to like escalate to an actual dermatologist and seek help. And then challenge number 2 is our CV model integration, but we got G right here to talk about that pretty soon. So what's next for MVP this semester, or not MVP, just Claire in general? We're gonna finish our front end as soon as possible. Currently, I'm waiting on Apple to get approved to like actually upload the app. I gotta pay $100 for that, but that'll be done like hopefully in the next week. And the data collection thing, I feel like it can never be done. It's going to be like an ongoing thing, no matter how far we get into Claire, because it could always be optimized or add more things, so that we can make sure our model is as accurate as possible. And now is around the time where we're about to pivot into like our second phase, where we are training our own CV model. And this is important to make sure that we're not just building a GPT wrapper or something like that. We spent a lot of time curating this data, and I'll pass it over to Jeet now because he's about to be our CV team lead along with Sharif. So.
Thank you. So for the CV model, while we were supporting with the backend with like all the history endpoints and like all the data points that were like getting inputted, we were also keeping in touch with all of the data team that was like gathering the data for us, so we can have some kind of idea on how we can train our CV model and what kind of format it would be. So it was already in the background, and now we're gonna go full force on it in phase 2, and we're gonna have our own CV model. There are some pretty interesting CV models I researched on huggingface.com. Some pretty interesting models on other open source websites where you can basically contribute to open source models. And yeah, we're going full throttle with PyTorch and Python and getting that ready up for the phase 2. Yeah, that's our plan. So thank you. If you guys have any questions, please.
So after spring break, this app, hopefully all of you can actually start using it. It'll be under the GBT model at first, but if you guys like the concept, this will be accessible to everyone in this room through the app store.
Yeah. Sounds good. I mean, I guess I open the floor now to any questions or any concerns that you guys think. Sure, go with you.
What I'm curious about is what would be like an example use case for this product? For example, if I take a picture of my face, upload to this app, or do I get back like a recommended skincare product? Do I get back like a list of ingredients I need to look out for?
Yeah. So I guess like I did have it in my original pitch. So a use case would be like, yeah, sure, you take a picture of, let's say, like your forehead because you have some bumps that you can't seem to get rid of. Claire will tell you what it thinks it could possibly be. And it'll tell you like what habits, like I said, it will already have like context on the user and like what their current routine is, like what their lifestyle is, maybe even like eating habits, things like that if you choose to upload it. And so it'll tell you like what you're doing that could be potentially causing it and you know what you can do to address it. And then if like a product is necessary, it'll have like recommended products and stuff directly linked there. And of course, through all of this, Claire knows not to diagnose the user ever. So like the guardrails was an important thing to put in because, you know, obviously there's some legal issues there. And there's always like on our front end, there's like hard coded like disclaimers saying, you know, always check with a healthcare provider if you're unsure. Yeah. Any other questions? Yeah.
How do you guys train the models for the backend? So you guys have the images, but you guys said you guys had used ChatGPT.
Yeah, so currently we do all we're using is the 4.0 mini model, and it already has like an image, like a CV model for it. And so yeah, we're just implementing the API, and we do have like what we're using for the MVP is our like ingredient like compatibility table, like our product recommendation table. There's a couple more, right? Like skin type, like essentially everything but the images is what we're using for our thing, and we're putting in a bunch of like guardrails as well. So that's for like the MVP, and then for the long term, we're training our own model using like we have a couple gigabytes of images now from like diverse skin types and skin colors and you know a range of things that we're going to be training on PyTorch. I believe G also like tested like a practice CNN to try and like create you know our own CV model, and so we'll talk about that.
Yeah, so to make sure that we understand how we can get the image input and how we can materialize in a way that it will make sure that it will input the image and will give the right output to the user, I basically started with creating a CNN classifier, which is like the most basic form of the CV model that we're trying to make. And based on that, going off of that as like a base model, we're going to expand more on that and make sure that we have like more options as much as possible for every type of user that may use it. Yeah.
All right. Is there any other questions? Yeah.
Two things. Do you guys have a plan, like, in order to generate revenue from this, or is there like the business side? Have you guys thought out much?
Yeah, I mean, there's been early talks on it. I mean, currently, you know, there are like product recommendations in the app. Currently, they're all just like formatted to be like Amazon referral links. That's just, you know, like beauty products on Amazon, they give us about 10% of any purchase through our link. That's like good enough to fund the API key for now. But like there haven't been too many talks down the line. I mean, if we do train like a successful model that can be sold to other companies like Curology that do create like custom curated skincare like products and stuff like that. So maybe like getting acquired or something down the line. You know?
That's cool.
But like I guess we're running out of time here. I just want to make some closing statements that you know there's a lot of applications of AI in healthcare, And I think like, especially nowadays when like dermatology advice is like powered by influencers on like Instagram and TikTok, there's a lot of misinformation, and access to dermatologists it's like either, difficult to get your hands on them, or it could be expensive, So I'm just excited to see like the potential of Claire and like where we can go with this. And I got a great team with us, I think around 12 members. So yeah, I'm really excited. Thank you.
All right, guys, I'm happy to introduce my friends Joao with NeuroDiffusion Project. Please give them a round of hand.
Thank you. So we are NeuroDiffusion. I am Joao.
I'm Aditya.
I'm Shahila.
And I'm Katie.
And we're here to demonstrate our progress that we've made throughout the semester. So, how do we Right. So quickly, just to go over what we are the focus of basically getting some type of image or imagination to an image. We're trying to basically bridge the gap between mind to a canvas of some sorts. So this requires us to essentially just tap into the mind through EEG or fMRI and generate some type of image using latent diffusion models. And currently we are focusing on trying to elevate the current baseline, which is focused on more perceptron to imaging, but now we're taking a further step into imagination, essentially. So I'm gonna pass it on to
Yeah, so we read various papers like for our like preliminary like research and stuff, but these three were like the top ones that we're like using for our project right now. The first one is MinDViz, which is was done by I think Stanford graduate students, and they reconstructed images using fMRI brain signals, which is more of like a more concentrated scan. It's more expensive. It takes longer. It's hard to access. It's a big machine, but it does produce like very clear brain signals. They were able to produce like really well images using the like latent diffusion, and they also mask like their brain signals. But because fMRI is slower and harder to use, we decided to use like EEG, which the second paper talks about. Brain data image was like one of the earliest papers that we found that was able to get like really good like accuracy in like EEG to images. So the images that they produce using EEG signals, which are like more messy, they contain like slight muscle movements, like blinking and things like that. So the fact that they were able to extract like context relevant EEG features and then actually produce like clear images was a really good sign. But they did use more older models such as like VAE and GAN. And the new paper that we found more recently, I think like 2 years ago, is Dream Diffusion, which generates images directly from EEG signals, but they have a more modern pipeline. I'll explain the pipeline later on, but we saw the results, and the results are very clear. Yeah, so that's the model that we're decided to build upon. Essentially, they start with like raw EEG signals, and then they'll mask a certain percentage of them, and it'll go through an encoder where the model will reconstruct those signals, and then it'll be denoised and placed into a latent space where it'll be in a latent space with a stable diffusion. So stable diffusion has a text image. They have text image, so they'll try to the model like tries to align the text to image. I can't think of the word to the EEG latents. Yeah. So yeah, again, like the first step is that they'll mask a certain amount of signals. So this way it'll that way it helps kind of clear up like the blinking and like the small muscle movements and reconstruct those signals so that we get like a clean EEG signal. And then we can use those features and then embed them into like an EEG to the latent space. And then we'll also use clip to align like the EEG in the latent space so that it acts as like a mediator between like the stable diffusion model, and then of course the stable diffusion model has a text to image pre-training, which so essentially we're just Dream Diffusion like will try to create EEG signals like similar to like the text to image pairs from the diffusion stable diffusion model.
Okay, so this is just our tech stack, basically the software and hardware that we're going to end up using throughout this whole project. It's very similar to what they use, and inevitably sort of downstream we're going to end up using it as well. So sort of like Aditya said, Stable Diffusion is the latent text-to-image model that we're going to end up using. Worked really well in Dream Diffusion. The only issue, or one of the main challenges, was that the alignment between the text and image was kind of hard to learn. So they ended up using Clip for alignment, which is that contrastive learning or language image pre-train. What that essentially does is it kind of aligns the text and image and ends up creating a better quality image at the end of the day. So in the actual paper, they used the text encoder to kind of create better descriptions for each image. And then along with the image encoder, optimize the EEG embedding representations for better alignment, so you get better images at the end of the day. Next is EEG Lab and MATLab. I'm sure maybe some people in this room have used MATLab before. It's essentially a computing model. Allows you to, computing platform. It allows you to like analyze data, create algorithms, models, stuff like that. EEG Lab is very specific to electrophysiology data, so that is what the EEG will be run through. MOABB, it's a very long name. It's Motivated Open Source Alliance for Benchmarking Brains. It's essentially an open source repository of EEG data sets that allows you to sort of refine newer algorithms, and it's kind of like calibrating in a way. And then ImageNet EEG data set. This is a little bit more specific to the paper itself. Someone else is going to go into that a little bit better later on, but it's kind of like a data set that's specific to the experiment that they did in the paper. And then lastly, the EEG headset is what was used to record the data itself. So this is the current research and sort of what we wanted to do and tweak for our project. So currently they are essentially using Clip and Stable Diffusion to do the whole text-to-image processing. The experiment itself uses 2,000 images in groups of 50 images. They flash each image for half a second and then give the person a break. And that whole time period is where the data is being collected. So what we wanted to try to do is to introduce some sort of time delay in between the image being presented to the subject with a time delay and then going into the recording aspect. So this introduces the time delay, of course, and then along with that, new parameters. So kind of going into that a little bit more. This is kind of like where we are at the moment. So we are still looking for the headset itself. We've reached out to a few departments on campus, like nursing, kinesiology, psychology, places like that. We haven't really heard back too much, so we're still looking for an EEG headset on campus. Campus would be ideal because they have a little bit more of a controlled environment that we can utilize, so those control parameters will be a little bit more standardized for our experiment. And then the current plan, kind of like I said, we'd flash an image, probably have some sort of black screen in order to give the subject something to look at that's not the actual image, and then prompt them to think of that image, and then that time frame would be for our data collection. And in terms of parameters, we have a few research papers that have thrown out like a couple numbers that we can think of, but in terms of specifics for our experiment, we're not quite there yet.
So we have some difficulties locating an EEG headset, so we've been doing more research on the data preparation and collection. So so depending on where we borrow the EEG data set from, they might have their own location and protocol. So we're just looking into what's shared between different protocols. However, again, this might change. Some basic steps for EEG data collection include random pilots, which are basically test trials for collecting EEG data before being tested on any subjects. And then we'll do polynomial, which means that when the subjects are being tested, we make sure that the electrodes are properly connected and there's no
Mind holding it a little bit closer?
Oh, sorry.
Perfect.
And then we'll do statistical tests in order to ensure that the EEG data set is sufficient for the pre-processing pipeline. There's some steps in the pre-processing pipeline, and these can change depending on the lab that we might contact. However, like some basic steps that are shared amongst pre-processing pipelines using EEG lab are applying filters between 1 Hz to 95 Hz. And the purpose of this is to exclude artifacts, which are blinking, muscle movement, things that interfere with the EEG waves that we're actually interested in that are linked to cognition or image processing. The next thing we'll do is re-referencing, and this looks at like a neutral control. It's usually behind the master point. There's like other ways to re-reference, but that's what we were looking at. And then there's downsampling, which basically reduces the sample size. It's better to have a larger set of data that we can reduce and look at over. Then we'll project large artifacts that basically maybe, again, movement that interferes with the EEG data that we're looking at. Then we'll run ICA and project confidence, which is basically the same thing. We remove large artifacts using the data.
Alright, so our current progress with the code and model itself is focusing on what we call phases. So we dissected this dream diffusion framework into 4 phases. First one is kind of like your data pre-processing or configurations. Second one is focusing on masking the EEG data set. Third one is linking the latent diffusion models to the data set. And the fourth one is generating the images. So the area that we've identified that we will be contributing onto this framework is going to be primarily in the first phase and the second phase, where we're going to be altering the configurations to benefit or to fit into our data set. And the second phase is essentially we got to make sure that the masking is correlated with that kind of time gap that we're providing, where we have like that brief moment from the user or the subject seeing the image to the subject imagining the image. So we got to make sure we account for that and alter that into the framework. But aside from that, since this framework is so well done and essentially basically generates high defined images purely just from its perceptron, we don't have to tweak too much of that EEG to latent diffusion process essentially.
So this is an example of the ImageNet dataset that we were looking at earlier, and this just shows how the data was collected. So basically, all the data is between 5 and 95 hertz, and the EEG recordings were collected from 6 subjects, so a pretty small sample set. They were all members of the lab. 2,000 images were shown to these subjects individually, and each was shown for 0.5 seconds before a 10-second break after 50 images were shown continuously. And there was a blank screen between each image. So training and testing are performed on the same subject, which is why it is normal and better to use a smaller sample set or smaller number of subjects. So some challenges that we have faced are to collect the data, we need an EEG headset. We have contacted, again, several departments, kinesiology, nursing, and psych, but we haven't gotten a positive response back, so we're looking into contacting individual professors and labs. Once we do, they might have their own location and setup, so what we're going to try to do is collaborate with the professor in the lab in order to find like an ideal process of collecting data. However, these are some of the challenges that we predict we'll face in that process. It's difficult to find parameters for clean EEG data collection. The problem with EEG data is that it's a lot more noisy than fMRI data, and some portions of our project intend to address that. We also need to be very careful about collecting our data. So in terms of image selection, 600 to 2,000 images is about the benchmark for showing a subject. And these images are again distributed among different classes in order to have a good sample size. The sample size for subjects is between 6 to 9 subjects, so it's very small. It can be lab members, so it doesn't have to be randomly collected. For our project, we intend to use all members of the team, and there are 6 members of the team. We have to usually write down a survey or fill out a survey beforehand to make sure that attention and memory are sufficient for the project. Other parameters that we might have to control in the testing environment include temperature, light, the subject distance from the screen. All these like very subtle parameters might actually affect the quality of the EEG data. So it's very important to keep it consistent throughout the course of collecting data. So another parameter that we'll have to change that we talked about is the total time frame and delay with recording. So normally it takes about 60 milliseconds to process basic visual information, including shape and color, and it takes a little bit longer, 100 milliseconds, to process complex visual information. So this is just looking at an image and understanding it. It would be different if you received audio and then you had to imagine something. So we'll have to adjust those parameters. And if we show a large data set, we also have to account for fatigue. So those are things that we need to consider during the process of collecting data.
So to finalize our presentation, essentially what we've done so far is from basically ground zero, we've collected a good sample size of research and understood what the current baseline is. It's currently just perceptron to image. So that means that a user is looking at an image and an image is generated from that. We want to take it one step further and essentially bring an imagination into life, where we're taking away that image and the user itself is generating that image strictly in their minds. This will be, as we mentioned, will be needed utilizing EEG headsets that we're looking for. But aside from that, we are currently making preparations in every single area that we can. So we're making our proper scripts to conduct these collect data collection. We've also started working on understanding the framework and also tweaking it to benefit our data set once we collect it. We're just making all these preparations to make sure that once we have this headset data collection or our proper data set, we are ready to just put it in and output some type of images. And that would be essentially the end goal, is to get some imaging and see if this idea can come to life. And maybe we can even take it a step further. But aside from that, thank you.
How much does the EEG headset cost? Like if you were to just get one?
Cheapest, like really cheap, like 6 caps is like 500. But like the ones that they use in experiments, those like, how many caps? Like 128, 64 caps, a couple thousand. So that's the reason why we're reaching out to faculty. Yeah.
Have you guys considered reaching out to like student clubs? Because I think like Neurotech at Santa Cruz, they have an EEG headset, and Santa Cruz isn't too far from here.
We could try reaching outside of San Jose State. I think we're trying to stay within San Jose State first, because I think I asked this with Advait. We had to kind of have some additional steps in order to have outside faculty use or something like that. We can always look into that, but thanks for the recommendation.
Quick thing, like I was wondering when you mentioned like I think you guys were mentioning for the EEG, like this would be like an ideal control environment. Not in the slides, but yeah, I'm just saying. I was wondering if you like, are you looking? So when you say you're collaborating with professors, are you looking for like student subjects essentially that you're testing the EEG on?
We don't really need a large sample size or subjects, so we're not looking for any students. I think like a lot of studies use lab members, just because we need to do the training and the testing phase on each individual. So it's better to have like they don't have to be randomly selected.
Yeah. If you do want to join, we could maybe make some accommodations depending on the lab. Okay, Matt.
So first of all, I think that's one of the most impressive projects the club ever had. Suggestion I had for you for further EEG headset search is to include the video of this presentation. Send it directly to people. And then the question I had is, I missed some of the presentation, but if you already have the data, why do you need to collect additional data?
So the data that's currently that these experiments use is strictly perceptron. So that means that the user or the subject is looking at the image while the data is being collected. We want to take that step further where we're taking away that image, giving the users some time to think about the image they just saw. So it's a minor change, but it's essentially a major change in the sense that the user is not perceiving and it's strictly coming from their thoughts itself. That's the data. That data set, unfortunately, we cannot find. So that's the reason why we're focusing on collecting it ourselves. And also it would make it so that we can also test and see our own imagination coming to life, essentially. I feel like that'd be more fun. Right?
Yeah. Thank you.
Yeah.
No, I need them to talk to me after. We have fun.
But is was fun. Yeah, I know you. Someone mentioned to me the first time on the pitch that you guys could allocate like 500 max. So that's kind of our backup, just in case. But yeah, I am aware of funding within the club. Oh, CS department. Oh, okay. Okay.
You should follow up after this presentation.
Yeah. Okay. We'll do that.
We've been working on it.
His suggestion about SJSU does not have neuroscience department, right?
Yeah.
So the closest one would be more towards either psychology, if you wanna go with the setup overall, or with some of the faculty works actually for EG data. So we can connect you to them to see how their whole setup they have. Maybe we can utilize some of their environments.
We have done some research into which departments would have EEG data. I think these two have done the most work in it, so they can explain.
Could be some
Yeah.
from I have to retrieve faculty, but like it could be mostly from mechanical department or something like that. Some of their faculty actually work.
We think kinesiology would be the most likely department. So are we still waiting to hear back from them?
Yeah. So we had reached out to like a couple professors, like at least I reached out to a professor. Actually, we both had within like a bunch of different departments on SJSU's campus. A lot of them pointed us in the direction of kinesiology, and so we were wanting to go to like the department head itself. So we're probably gonna end up going tomorrow in person.
Contacts there, or we should talk to them.
Yeah,
I think help would be nice in general.
We don't know exactly the direction to go. We're just kind of checking we're checking every single box that we can. But yeah, assistance would be helpful with the CS department if possible. Huh? Yeah. Okay. Yeah, I think one of the professors said that there was some Stanford lab, but that one's like a really low % chance of us getting it. Okay, one more question. Yeah.
Yeah, BB has a professor that her background in neuroscience. She's the first time teaching here.
Bean? For which department or?
Medical engineering.
Medical engineer. What's her their name?
She's she's working on her PhD at Stanford.
Okay.
But she has a neuroscience background.
Okay, we'll take a look. Was yours kind of like a similar recommendation? Or?
Yeah, but there was because last year during this Berkeley's hackathon, there was a project that won that basically they just reached out to. There was an EKG or EEG headset like company in the Midwest. They just reached out and was like, hey, we'll demo your product before a hackathon at Berkeley, and they just sent them to them for free.
Okay.
So I don't know.
We'll look into that. Thank you so much for all the recommendations. That really helps.
All right, great presentation from NeuroDiffusion, right? NeuroDiffusion, very exciting project, awesome. All right, everyone give Ian a round of applause. He's gonna present his project, Obi.
Hi guys, so when I first pitched this project, it was supposed to be an Obsidian companion. So basically, it was just supposed to be an Obsidian extension that basically takes all your notes, indexes it, and then you can basically retrieve it and ask questions on a local model. But since I've been working on the project, I realized that this the scale of the project needs to change. It actually needs to be a lot bigger because while I was working on the project, I realized that basically by hosting your own model and indexing everything locally, you actually have access to a lot more tools than I originally anticipated. So so the use case now, I'm going to change it from just for students and small businesses. I'm going to target basically anybody who has private data they don't want to just send out randomly. And I think it can actually work. So right now it actually already works. Like I think most of the features that I want, with the exception of the step 3, which is the like whitelisting, blacklisting. Everything else already works for the context. So I'm thinking that maybe I just include, first of all, I need a little bit of a better understanding of how embedding works, because right now it only uses the embedding models, like base embeddings, but there are some, I saw there were some other better ways of like basically dividing the files into different types of buckets of knowledge. So then you can basically choose, hey, like depending on which workspace I want, I can do different things with it. So I'm just gonna go ahead and show you guys a demo real quick. So went ahead and
Use full screen. Yeah.
so basically, right now, if I go ahead and
Could you
connect
please
to
speak in the mic?
Oh,
thank you.
So go ahead, if I right now go ahead and choose this file, which I put a bunch of docs in there, and it's basically just full of gibberish that you have no way of like searching up online or it could possibly be in the training data. So I'm gonna go ahead and just open it, and basically this will load and index all the files. So now if I go ahead and go back to chat and I ask a question about it, so right now everything is happening locally. So if I go ahead and go to activity monitor, you can see that us is generating the response. Yeah, you can see that us is generating a response. The memory is going up a little bit, but this is only a 16 gigabyte Mac Air on an M2 chip. There's no there is absolutely nothing that's happening. Like in terms of hardware, there's absolutely nothing fancy that's happening. But what I was really impressed with is that because I used Llama CDP and SQLite and a lot of these really lightweight models, and I also used the Quinn 2.5 or 3.5 2 billion model, the entire thing basically only causes the memory to go up about 2 gigs. So you can actually run this on like a MacBook Neo and still get away with it, which I was really impressed by. And as you can see, it extracted the relevant files from the files that I indexed earlier from here. And it basically generated a response completely locally. So it never needed to go and ask for an API key of any sort. And the response time wasn't too terrible either. It was like 3 or 4 seconds. And I just thought that was pretty great. So that's basically the super basic MVP right now. It will go ahead and based off of the semantic embedding, extract the files and then use it as context and feed it to our local model. And this is how it basically works right now. So basically we have a choker, which is a file watcher, thanks to my file watcher team. They will keep track of new files and basically change the local database based off of which file was changed or deleted. And it will go ahead and embed it and put it in our vector database. And then for the user query, it will use the same embedding model, do a vector search, and then it will generate the prompt. And I still need to add the blacklisting and whitelisting, which basically will go ahead and find the chunks. And the data is all labeled already, so it'll know exactly which file it is from, and it'll go ahead and delete that from the context window. So if you don't want, so if you feel like that a certain file is not relevant, you can go ahead and just blacklist it, and then it will just never access that file ever again. So in terms of our tech stack, we use Electron by React for the front end, and then for the sidecar, we use Llama CPP. Super great tool, just really lightweight. And Quinn 3.5 is our chat model right now. For its for how light it is, it's got an insane context window. It's like, I think right now we have like 250K tokens, which is like I never expected that for such a lightweight model. And for an embedding model, we use the domain embedded. So for the next steps, first of all, I realized that in order for us to do anything that requires sensitive data, you need some type of security. So like, for example, if I want to go ahead and access tools, for example, like, hey, can you go on the browser and check my like finances? It will need access to like other tools, for example, like Bitwarden account, or like login passwords, et cetera, et cetera. And but the thing is because it's an access to the kernel, you can pretty much do everything that a person can, and I think that's pretty fantastic. And for the tool calling, I'm thinking of extending this from beyond just like a desktop app. I'm thinking that maybe we can link it up to like a web browser so that it has access to the HTML that's generated or that's basically sent to every single browser and basically see what's happening in the browser. so that if you go ahead and go like, hey, can you go on chase.com and chase my like search on my finances, you basically will have a model that can log in, like target a div and basically log into it, and then basically grab all the information they need. And then for the external AI, I know that a lot of people right now, they are really passionate about like OpenClaw and self-hosting models, but there's also other people that don't want to go through all the hassle. So because right now, it really is, I at least I did a pretty good job of separating the concerns of front end and back end. So if I want to right now, I can probably link up Gemini and like just go ahead and still use the exact same architecture I have right now. And for device linking, as I said earlier, a Chrome extension would be great, and maybe also in a mobile app. So I'm also looking into where you can basically from your phone remote control your computer to do some tool calling, and that will be in the future. And yeah, does anybody have questions?
I understand that your scope changed quite a lot, but I'm just trying to understand where does it end right now, because initially the pitch was very clear on a system for Obsidian Vault, and now you're talking about document embeddings, but now it's also for small businesses. The tool also goes online. So what is your scope of the application now?
So right now, it already handles text files and markdown files very well. And for Obsidian, because how Obsidian files work is that they have this little like users, they can tag the data themselves and be like, this node is about this. And because the way Nomadic embed works, it already handles that super well, and it will always like grab the closest file with like a very high accuracy. I think in terms of distance, it was like if I just put like a hard if statement, literally I just go, if the distance is less than this amount, it already does a great job with those markdown files. But the thing is, I realized is that if I want to push this to a wider use case, so not just somebody who already has like an Obsidian Vault setup, people will come in with all sorts of different data. So right now, something I'm looking into are like GNS, where basically they can look at a PowerPoint slide, and it'll be like, okay, I think this is what I think is happening on the slide, and store that information in chunks, so that when you go ahead and retrieve it as well, it'll still be relevant, if that makes sense.
And how does it tie up to this online web browser functionality?
So the problem right now is that so much data is scattered, right? And that was something that OpenClaw tried to solve. It was that basically you have emails coming in, you have discourse coming in, you have like slides coming in, et cetera, and but the thing is like for OpenClaw, what it doesn't do that well is that it doesn't handle the noise very well, and that's because it's linked up to literally everything. So what I was hoping with this is that you can basically, it's like, I don't know if you've ever gone through the same workflow of like creating a folder on your laptop, and then in that folder, just everything related to that one subject. So it'd be like, if you're writing an essay and you're going through and finding research, just throw everything in a folder, and then like you write the essay later. So right now, if I go ahead and I want to do the demo, but like it's a little hard to control it. But like if I go ahead and throw in like a couple PDFs, it'll go ahead and extract, or not PDFs, markdowns of like research papers. It will use that as context already, and it will just go ahead and generate me an essay, and I can basically constantly do my work, and the data is persistent, and I own it. That's the most important part. Yeah.
Okay. Thank you.
So I do have a question. I missed your first slide. So what is the business perspective kind of point of the project? So the tech, it's fine. Just like what are you trying to do?
So originally, it was only for people who they already have a knowledge base on their computer, right? They have, so say you have like a ton of notes somewhere, and you want to search through these notes in an efficient way. But now I realize that the scale of that is actually, it's good, but it can be a lot larger. Because right now, using SQLite and running it on a literal 16 gigabyte memory like Mac Air, it already, I looked into it and you can already embed up to basically 100,000 files. And that's a crazy amount that's something I didn't expect. I didn't expect it to be able to handle that amount of data and search through it effectively, if that makes sense. So now I'm realizing, okay, if this is something that can be done on one laptop that's this small, you can absolutely throw in like a crazy amount of data and still, like if you're a small business and you have like say a bunch of like Excel sheets, right? And these are like super huge, like this is a huge amount of data that's accumulated over the like last year or two. You can still throw it in and just ask it questions. And I think that's pretty impressive. But the thing is like the data right now, the file formats that I'm supporting right now is only markdown and text files. So I'm working on expanding that so that it can include other file